Hello and welcome to Iron Middle, our weekly live stream where we discuss all the things related to the Tagemittal distributed database for accounting. So, as usual, don't expect this stream to be like, super high quality production. That's not the goal. The goal here is to just really show you how a modern database is getting built. We'll be doing aim and har, and we'll lose our way and go in circles, but eventually this hopefully will help us to understand how you could take your favorite systems programming language, take your editor, and build a modern distributed system from zero. We've been doing this for quite some time, for more than 100 episodes, and recently we increased our reach to start streaming to more platforms. And that's actually good because today we are starting a new fresh arc in our journey. So the goal today is to, well, not today, for like today and next week and for, I don't know, maybe like 3-4 episodes, is to understand how Tagemittal deals with pending transfers with a timeout. So maybe it's the time to draw some pictures here. Let me see if I can actually draw any pictures at all. Where is my picture drawing thingy? It doesn't work. What's going on? Where is my tail draw? Just a sec here. It wants to check if I'm human and still doesn't draw it. How do we call this, oh dear. Okay, let's go back to Excalibur land. Okay, sorry for the delay, but we now should be all set. Okay, so payment transfers. So like, normally what you can do is that you have like account A and account B, and you could just send some money from A to B, right? In some cases, you actually want to do kind of like, a multi-stage kind of iteration. You want to make a promise that you are going to pay. So, and this promise is called like, payment transfer. So what does it mean is that when you create such a payment transfer, you reserve $100. And then at some point later in time, you go and you say, let's post this transfer. And you actually, okay, maybe this is not the right way to do this. No, I don't, what's going on here? What's going on here? This is not what I am. Yeah. So what's actually going on? Like you post existing transfer. So like at some point you like make a promise, and in some later point you like say, okay, let's like do this promise. And in this case, this $100 goes to B. Or you could also say that, hey, you're not posting, you are voiding this promise. And in this case, $100 goes to A and then can be spent elsewhere. So why is this kind of primitives useful? Well, first of all, just for like various like confirmation workflows where like you first check when the user actually has the money to like pay for something, and then you show like confirmations in here. Are you really like, you could pay this, yes, but do you really want this? Another case where this comes up if you want to arrange some kind of like multi-party payments where like you have like A, B, C, and D, and they all want to pay like $100 to some common pot, but only in the case where everyone actually has $100 available. So in this situation, what you do is that you first create 4 pending transfers. And if all of those pending transfers created successfully, then you go and post all of them. And you know that posting a pending transfer cannot fail. And if someone doesn't have the money, then like that pending transfer fails, and then you can avoid everything else. Importantly, this also can be made asynchronously. So you don't have to require everyone to pay $100 at the same time. Because if you want to do that, just linked transfers would be enough. You could like A commits to paying on Monday and B on Tuesday, etc., etc. And like eventually, when everyone is ready, you post the transfers. Okay, so to handle just this aspect of data model, we don't actually need anything particularly fancy. So if we look at our data structures here, you see that in the transfer, we have amount and we have a flag, and the flag can be seen here. This is a pending transfer. And then in the transfer, we also can say, hey, this transfer is a posting transfer for a preceding pending transfer or a voiding transfer for a preceding pending transfer. So to handle this in the transfer, we just need 3 bits. To handle this in an account, we need a little bit more. So we actually need to split account balance into posted, which is kind of your normal balance, and then pending. So pending balance is reserved balance. When you post the pending transfers, you increment pending and posted. And when you actually post a pending transfer, then the balance gets rolled over from pending to post. Actually, let's just see how that works in state machine, shall we? Okay, I think my font size. Oh yeah, okay. So this is better. Execute, create. So somewhere here we should see create transfer. Yeah. So where do we actually do this? Where do we check for pending? Oh, right, yeah. So if the transfer is pending, then we increment pending side of the balances. And if it is not pending, we directly increment posted. So that's it. Now, let's see. Where do we? Yeah. So this is creating a pending transfer. Now we accepting or rejecting it, or posting or avoiding. That's a separate function here. And what we should do here is that we should look up the original transfer, I think. Yeah, so this is the transfer. Well, okay, this is something I glossed over, but let me say this loosely. So there's 2 operations. First, you create a pending transfer, and then you resolve it. But to resolve a pending transfer, we also use a transfer object. That's it. Okay, so we have T, which is our resolving transfer, and then we have P, which is our original transfer, which was pending. So there's some logic there, you could not necessarily, post the full amount or whatever, but it doesn't matter. What matters is that once this happens, so you roll over the changes from pending to posted. So you, I wonder if this is the only place in our code base where you need decrement account, because usually we don't have negative numbers. So you decrement pending, and you increment decrement pending on both accounts, and then somewhere, yeah, and then you decrement posted. So this is not what the current episode is about. This is just very simple financial transactions, business logic. What we are going to discuss today is an extra feature there, and the feature here is timeout. Timeout equal 1 minute. So, like, you know, when you make a promise, like the promise might get stuck. So in some cases, it's advantageous to actually like at a timeout, saying, okay, I'm making a promise, like I'm committed to paying $100, and I will make a decision where I'm actually doing that or not within 1 minute. But if I don't make a decision, then my default disposition is to not pay. So you want to like order reward transfers after time. So and that means that, you know, that like even if the user doesn't do anything else in 1 minute, something has to happen. Like, you know, like this, like, you know, so where this something is unlocking the balance. So when you make a promise, this, like, you know, $100 is locked. And if nothing happens after 1 minute, we actually want to cross this over. Well, there is no crossover point here. Cross this over and like unlock this balance. So why this is a fascinating feature for Target? Well, the key idea of target middle, and let me like actually write it like, you know, in bold red and like XL font, is static allocation. We want target middle to be like incredibly reliable. We want target middle to be a yardstick to measure reliability of our system against. And reliability comes from robustness. And robustness is an ability to withstand the unexpected, behave in an acceptable manner, not only in the happy case, which happens 99.99% of the time, but also behave in a reasonable manner when all kinds of unexpected things happen, to not completely fall over in 0.01% of the cases. And to do that, you need to have predictability. And static allocation is a forcing function for that predictability. So the idea here is that for a really reliable, really robust system, I might use it at some point in the next 5 minutes. I'm kind of like, you know, I'm creating a pendant sneeze there. I might post it, or I might void it, or it might collapse. Yeah, so the idea is that to make a system robust, you need to make sure that you know all the limits. You don't want, like, you know, to run your system until the edge of its capabilities, and then over the edge, because if you kind of like overshoot what the system can actually handle, by default, what will happen is that the system will crash. So you always want the system, instead of crashing, to start politely rejecting the overload. And to make that possible, you actually need to encode the knowledge of the load in the system. The system needs to know its own limits. It needs to know where to stop. And for robustness, that means you need to know the limit not only for, like, you know, the core data structures, but actually for every single thing that the system does. But if you know the limit, then you don't need dynamic resource management, because you could actually just allocate everything precisely up to that limit and then just carefully manage that finite amount of resources, which means that you don't need dynamic memory allocation. So, okay, that's kind of like a pitch for Target approach to reliability, which is enforced in static limits. Now, why do timeouts create a problem here? Well, to understand that, we need to understand why we don't have a problem without timeouts. And the reason for that is, by default, Target has static limit on the message size, which is 1 megabyte. No. Oh, why does it not do what I wanted to do? Like, if you send a message to Target, you could send like at most 1 megabyte. And that means that a message is 8,000 transfers maximum. So that means that to process an atomic batch of changes, you need only a finite amount of resources, because you know that, hey, the worst case, you are going to have 8,000 transfers, and then you could just allocate memory to serve that amount of transfers and nothing more. So that's how static allocation works out in the happy path, by virtue of atomic input to the system being limited to 1 megabyte. You could still send multiple inputs to the system, but they will be processed one by one, and you will use like only 0.1 memory for each of the messages. Now, this is fine. Why timeouts create a problem here? So imagine that we have a timeline. So this is T, and we have, like, multiple messages here. So this is like, 8K transfers. Okay, I probably need to make the canvas bigger here. So 8K, let me actually move this here. Okay, 8K, 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 8K. Yeah. So far every single batch is processed atomically, and it's fixed size, so we do certifications. But now imagine that every one of the transfers here is pending, and they all have the same timeout. So we have this kind of like let's move static allocation above deadline. So it is red as well. Deadlines are always red. And it so happens that every single transfer actually specifies the exact same nanosecond as a deadline. So the system works okay in this case, but by the time we reach the deadline, we actually suddenly get a huge backlog of work which we have to process immediately. And then this kind of like creates like a giant explosion, and everything dies. So that's a problem. So how can we solve this expiry? And okay, so if you are watching this live, then sorry, I will like spoil the answer. But if you happen to watch this recording on YouTube, this actually is a good point to pause the video and ponder this question: how you could solve the problem of clumping up of scheduled work for pending transfers in a system with static allocation. And the answer here is that like there is no magic. You can't just like like go and solve it. Like something has to give. And what we actually do in TigerBittle is that we don't, well, we have like semi-strict guarantee about this deadline. So what we do guarantee is that at this point, just after deadline, you can no longer post a pending transfer. Like, if deadline has passed, like, you do not post a transfer. However, we do not guarantee that your funds will be unlocked immediately. So usually we will unlock the funds like relatively promptly, but there is no strict guarantee. There is like some license. So let's maybe do this again. So we have like this timeline, and there is T1 pending transfer created, and then there is like T2 expiry deadline. So at this point, right before the deadline, okay, let's make deadline red. So immediately before deadline, you actually can post here. Then immediately after the deadline, you say posting fails, but then sometime later at T3, like what happens, like timeout voiding, default voiding. So parentheses funds unlocked. And this is the interesting case. So yeah, and so okay, this is kind of like how we make this problem tractable in a static allocation scenario. We essentially just smear the work to void all these transfers across like a larger interval, and we will be digging into the source code quite deeply really soon. But the idea here, like the way we do this, is that state machine on a tick checks if it needs to expire anything, and if it needs to expire something, it posts a special heartbeat state machine message which says, hey, please like expire like up to like 8,000 transfers now, and then like you go and expire this. So normally what happens is that you like don't use up all 8K expiry slots. Like there's like like 10 transfers that are expired, so you only expire 10 transfers, and that's it. But if like this real situation like happens, then you are expiring transfers like in well-defined order, deterministically, just over a larger window. Okay, so now let's dive into the implementation, because it's actually pretty fascinating. So we will start with our data model. inside transfer, we have timeout. And I want to emphasize that timeout is in seconds, because again, we don't guarantee super precise timeouts, and we kind of like signal this by saying, hey, normally the transfer timestamp is U64 number of nanoseconds, but the timeout is just U32 seconds because it is like lower cardinality, like lower precision. Okay, now in the state machine, when we post or void pending transfer, we go where, yeah, okay, we go and we check expiry. So we say, okay, this is the original pending transfer. This is its timeout in seconds. And if the expiry has already passed, so timestamp is like our current time, then we go and we say, hey, this pending transfer expired and you can no longer do anything with it. So this is how we make our timeouts semi-precise. When the timeout is expired, like, you cannot post the transfer, and that's like, ironclad, there is specific guarantee in the state machine. The more interesting question, what happens, okay, how do we actually unlock the parameters? And that will take quite some time for us to dig through, and our studies of the query engines actually will help us here, because I believe that queries, or like at least this kinds of machinery, plays the role into expiring transfers as well. So I think what we'll need is, do we have pulse here? Pulse, yeah. So what we'll need here is the pulse operation. So what is the pulse? Pulse is kind of like, well, it's a pulse. It measures a passage of time, except that kind of like we don't do pulse like every 100 milliseconds or like 1 minute or whatever. We rather like do like hibernation. So we only pulse when we actually need to pulse. It's kind of like, it's kind of like a pulse, but if there is no pulse, it doesn't mean that your database is dead. It might mean that it's only like, sleeping until something wakes the state machine up. So there's like two points here. One point is that when the pulse happens, this is a normal operation which is pumped through the state machine, pumped through the consensus protocol, pumped through all the logic. And part of the logic that gets triggered by the pulse is that, hey, actually, we need to expire some pending transfers. So in other words, whenever a state machine processes a pulse operation, it goes and sees if there is anything in need of expiring right now, and if it is the case, it goes and expires things. So the other half is how we actually decide that we need to pulse. And here the trivial solution is just go and always pulse things up. But a better solution, like a more efficient solution, is actually to, like, see if we need something expiring soon. And if we do need something expiring, then we do pulse, but otherwise we just say, okay, we kind of don't care. So the interesting thing here is that in this formulation, pulsing doesn't really need to be itself, doesn't really need to be deterministic. So again, there is, like, one-sided error here, is that if we do have something in the need of expiring, then we must pulse eventually. On the other hand, if we don't need to expire anything, then we can still pulse. It's just the pulse will be a no-op and will, like, waste some CPU time, but no harms done. So that means that it is enough for the primary to unilaterally decide when the pulse needs to be injected. Okay, so that is the long and the short of it before we get into the details. Expiry is non-deterministic. It happens on the pulse message in small increments, so every single pulse can expire only so many transfers, and it's up to the primary to decide when a pulse message can be injected. So you could think about it as primary injecting pulse on a fixed cadence, like every second or something like that. But actually what happens is primary is smart and it computes the next moment in time when it needs to inject the pulse message. Now let's dive right deep into the source code and figure out how this all works. And yeah, I kind of told you at the beginning how this is like off the cuff, like super unprepared stream of consciousness style of streaming. I must say that the first half of today's episodes didn't look like this. I was like relatively smooth talker, but now we'll start diving deep into the code and you understand that I understand nothing here. Okay, so let's start with prepare. Wow, okay. I even failed to open the right file. So we start with like the actual logic for handling is in the state machine, not in the replica. Okay, yeah, that's maybe also worth explaining once more. So what is TigerData? It is a database for, it's a distributed, durable, reliable database for financial transactions. That means that there are two parts. There is consensus protocol, the so-called VSR framework, which implements the distributed state machine. And then there is the very specific state machine, which implements double entry bookkeeping. And the state machine is like pluggable. You could take TigerData's consensus and use it with a different state machine. So the logic for, so the mechanism for injecting pulses belongs to the VSR protocol, but the actual logic for reacting to pulses via expiring pending transfers belongs to the state machine. When a state machine processes an operation, it does it in two steps. In the prepare step, the state machine does all the asynchronous I/O that it, well, okay, it's three steps. It's prepare, prefetch, and commit. Prepare basically checks that the operation is syntactically valid. Then prefetch takes this pre-checked operation and executes all the asynchronous input-output that is required to process the iteration. Then, after all I/O is done, a synchronous single-threaded commit phase is run, which actually applies all the CPU modification. Well, and the fourth iteration of this three-part execution pipeline is compaction, which actually takes the diff computed by the synchronous execute phase and asynchronously writes it to disk. Using like, well, it's kind of like hard to explain how exactly compaction works. Please see our previous episodes. Okay, so do we have multi-batching? Okay, so let's add multi-batching here. Multi-batching. Ah, okay. We do have multi-batching here. Let's also call it multi-batching so that we could. Oh, by the way, I think I should be able to cross out queries. We haven't covered our simulator for queries. Okay, we'll probably need to do this at some point later, but okay, let's maybe come back to the queries after we finish with this new arc, which is pulse expanded post. So this is today's arc. Okay, so when we prepare pulse, we don't actually do much. We just say, hey, we could expire at maximum like 8 key transfers. And this is by how much we advance our timestamp. What even happened here? So Agibito has a very useful notion of time. Like, you know, when you do consensus, you need obviously like logical time, which tells you which iteration happened before another operation. At the same time, when you actually are writing business logic, you could use the local time. You need to know, like, you know, is it like a Sunday, a Thursday? Is it like, you know, BC or AD, that kind of thing. The way we solve this problem is that we actually say, okay, DSR framework provides you not only with the logical time, the op number, which is like monotonically incremented sequence, but also with a physical wall clock time, which is the timestamp. And we implement, like, you know, if you go to our time, our clock, yeah, there is like this pretty nice comment explaining how our code works. But the long and the short of it is that we inject a timestamp into a state machine, which has actually quite a few guarantees. First, it is guaranteed to be roughly in bounds with real time. We don't say that, hey, this is kind of like precisely equal to real time, because we do not want to rely on like super high performance, high reliability and high precision atomic clocks or whatnot. We kind of like say, hey, like, you know, the time which we inject is kind of like in the vicinity of the real time, you know, maybe like a second less, a second more. But we guarantee that this time is like strictly monotonic. So even if like there is some kind of thing like a leap second or a, okay, this was like, it's my pen and sneeze. Okay, looks like it's wooded. So a leap second, or maybe like a day late savings time, or maybe like, operator just like manually tweaking the clock, we say, hey, if those things happen, like we still are going to provide you with strictly monotonic time. The second thing we do is that we say that, hey, actually, everything, every object, every event in TigerBeetle is tagged with a timestamp. And those timestamps are fully unique. So that's why when we prepare to execute the operation, which is comprised of thousands of atomic events, we need to figure out just how far we need to advance our timestamp to make sure that every atomic event gets its own unique timestamp. So for pulse, we say, hey, create transfers is just how many transfers we can expire in a single kind of like pulse message, and that's the amount of nanoseconds we need to advance our time by. Okay, then we go to prefetch. And I think, yeah, so, okay. So it was I was hoping that after our like query excursion, the code here would now feel obvious to me, but I understand that I don't actually like remember how buffer pool works or whatever. So I guess we'll do one more episode of like queries here, or maybe like 2, 3, 4, 10 more. But how long will it take? It doesn't matter. We have all the time in the world. So anyway, prefetch is going to do all the I/O. The thing that we need to do is to find all the transfers that expired up until the present moment. And that means that we need to run a scan operation, which is exactly what we are going to do here. So again, let's just try to understand this in detail. So what is prefetch? Okay, prefetch input is the message which we are prefetching. Prefetch operations pulse, scan lookup results. So this is probably something related to scans, which we'll figure out, and then we have like prefetch timestamps. Okay. So we want to fetch we want to statically size like the amount of memory for all the events we might want to prefetch. The complication here is, although the state is static, when we say that the state is static, it doesn't mean that it is fixed at compile time. It might also be fixed at runtime at the start. So what actually happens here is that TigerBeetle has like two limits. There is like statically encode absolute maximum limit, but then, and this is what we use for production. This is where like 1 megabyte message limit comes from. But then when you run in development, you also often want to reduce the amount of memory that TigerBeetle uses. And to do that, you actually want to reduce the size of input message. So there is like this comp time limit on the message side, which is about 1 megabyte. And then there is like runtime limit on the message size, which you pass on the command line. And then you take minimum of those two, and then you figure out how many transfers that corresponds to, and then you modify by the size of transfer, and you get the size. Okay, and then you take scan lookup buffer, which is under, how do we allocate this scan lookup buffer? We allocate scan lookup buffer size, and this is a max for all the scans we could be doing, which is so object size. Okay, so we have like object size, and then we say for this object, like how many of objects you can pack into a single message. Okay, perfect. Where we were. Which expire pending transfers. Okay, so we have this buffer. And then we have our transfers growth. And then we want to find all the transfers which are expire at, where expires at max is like our current timestamp. And we get buffer pool. So what is scan buffer pool? It's a pool of scan buffers. And scan buffer is a level buffer, and we have a bunch of level buffers. Okay, yeah. So okay, yeah, that's kind of like that makes sense. So as a reminder, scan is essentially like, you know, an iterator of the data we store in our database. Our database is based on LSM trees. LSM tree is comprised of multiple levels. So when you want to iterate over LSM tree, you want to iterate over each level, and then you do like a merge iteration across the levels to handle tombstones, to handle this effect that in LSM tree, data on the lower level of the trees actually shadows, it like completely eclipses the data below. And that's why you, like when you run a scan tree, you scan in one table at each level, and you need like an index block for this table and the variable for the table. Okay, so this makes sense. So we take a scan buffer, and then we do a scan with this buffer and with this like expires as and buffer. Where do we pass this? Okay, so we have scan, and then we do scan lookup with this scan. So what's expire pending transfers? It is expire pending transfers. What is expire pending transfers? It is expire pending transfers type. Okay, this is mysterious. Okay, so this is apparently just some helper. So what do we have here? We have context. Context should be expire pending transfers. Oh dear, it is an phase, and we have pause next timestamp, value next expired at. And when we do scan, okay, I'm getting you're serious. I'm getting lost here. Also, we are running out of time, so I don't want to completely get lost before we demonstrate. So I probably do want to save deep diving until the next next episode. So okay, so this is but this is I think is like the need we create a scan range is not what is scan range even? Don't remember ever seeing scan range. Do we use scan range elsewhere? Scan range. No, only in the state machine. So evaluator context. Okay, yeah. I feel like this is the weeds. So let's maybe stop this and prepare the ground for the future. So, okay, let's quickly recap what we've learned today. That TigerBit implements not only direct transfers, but also two-phase transfers, where first you can commit to making the transfer in the future, and then you could follow or abort your commitment. And well, what's kind of like the value of your commitment? Well, the value of your commitment is that you prove that you can actually commit. Like there's obviously, needs to be trust to make this useful, but that's the thing. So kind of like you basically, this is a way to avoid a time of check, time of use. You check that you have sufficient balance and you immediately reserve this balance. And then at a later point, you could use this balance or you could decide to not use it. This feature is useful as is, but it is especially useful if you could add a timers. If you could say, hey, actually, my pending transfer, my commitment has a certain time limit. And if I don't make an explicit decision to post or void my transfer, then my transfer gets automatically voided. This feature, the timeouts, creates a problem for TigerBit's TigerBit static allocation, because you could artificially construct this adversarial example of clamping things up, where you start multiple transfers and make them expire at exactly the same point, which feels like is an unsolvable problem. Like, you want to have a limit on everything, and here actually, like, you could unlimited amount of expiry transfers. The way this is solved in TigerBit is that we guarantee the expiry time only halfway. We do guarantee that when the deadline lapses, you can no longer post or void your transfer. But we do not guarantee that you unlock the balance immediately. Rather, like usually the balance is unlocked promptly, but if there is like literally the situation, the database will spend some time spreading the load across multiple operations. So we have like, this picture where you create transfer and then there is deadline. You could post right up till the nanosecond before the deadline, and you cannot post the next nanosecond. But we might have some extra time until we actually unlock the funds. So, and that's basically it. Okay, I'm super bad at clicking the right buttons on OBS today. So, super bad. That's basically it. Now, the way we actually drive the expiry, the way we take advantage of this laxity is that we say that we have a special pulse operation which happens sometimes. And when the pulse happens, we go and expire some limited amount of transfers, like at most 8K at one time. If pulse happens and there is nothing to expire, it doesn't matter. We just do nothing. So it doesn't harm, except for performance, to pulse more frequently than you need to. So pulses do not have to be deterministic. And then the primary implements like some smart logic, which we are yet to see, which makes sure that it only pulses when it actually does have transfers to expire. And how exactly that happens, we are going to learn next week at 5 p.m. UTC, live on YouTube, on X, or on Twitch. Or if you miss or just don't want to see the live version, you could always learn about that a little bit later on Tiger Beetle's YouTube channel. Okay, folks, hope you enjoyed it and see you next week. Goodbye. And now let me try to not mess up clicking on the right button on OBS one last time.